Very kind introduction there, and thank you again for inviting me to talk to you today. It's a great pleasure. So as Marcus said, my name is Gareth, and I'm an academic based at Queen Mary University of London, and I'm also a fellow at the Alan Turing Institute. If you're not aware of what that is, it's the UK's National Data Science Institute based in London. And if any of you, hopefully in the near future, are able to travel again to London, feel free to drop me a line, and it'd be great to invite you to the Turing or to Queen Mary to give a talk there as well. But anyway, what I want to talk to you about today is a topic which is very close to my heart, called the decentralized web. So some of you may have already come across this buzzword before, but it's an umbrella term that encapsulates a number of mostly open source platforms that have emerged in recent years that try to take common web platforms like Twitter or YouTube and create decentralized equivalents of them, which run in roughly the same fashion and give users the same functionality, but under the bonnet run in a more peer-to-peer fashion without that centralized control that you get in these mainstream platforms. So this is based mostly on a paper we published in IMC 2019. We also have a number of other papers in the pipeline. And before continuing, I should probably give a quick shout out, if I can get my change, there we go, to my co-authors. So this is Aravind Raman. He's currently at Telefonica. He's just started as a researcher. This is Sagar. He is a researcher now at Bell Labs. Perhaps some of you already know Emiliano and Nishant Sastry, who are two academics at UCL and now at Surrey. Anyway, what I want to convince you of today is one very simple fact, which is it is damn hard to decentralize the web. So I'm not the first person to make this observation. Does anybody recognize this gentleman here? By the way, I'll try to make this interactive, so feel free to unmute and shout out at any point. No, okay, so this man is a gentleman called Alexis de Tocqueville. He was a French historian and philosopher living in the 1850s. And about 170 years ago, he said the following: a push towards decentralization in the end became an extension of centralization. Does anybody know what he might be talking about, this particular French philosopher? Well, it might not surprise you to know that he was actually talking about the French Revolution, a very bloody period in French history where the people of France made a valiant attempt to decentralize the head of Louis XVI from the rest of his body. And they were fairly successful in this. And as part of this revolution, a major theme was trying to re-decentralize power away from the monarchy back to the people. But if you were to fast forward 20 years, what you would find is that actually that power had re-centralized again around, of course, the persona of Napoleon Bonaparte. And this, of course, occurs because often these efforts to decentralize face implicit pressures that push control back to central bodies. So in many ways, this is actually not so dissimilar to how the history of the web has worked. So if we go back maybe 20 years to the 1990s, the web looked very much like this. So you had various web servers spread around the world, and these tended to be operated by independent organizations and businesses. And each one was offering a different type of service. So for example, maybe this was some type of news website, maybe this was hosting a web forum, and maybe this one was some type of file sharing service. And we can see here that each of these different independent websites accumulated independent sets of users. So for example, maybe this forum has these 4 users accessing it, and this completely independent website hosted in another part of the world had this set of users accessing it. Now, this model actually was really cool. For example, it gave you much more symmetrical power structures such that the power of the owners of these servers were not entirely dissimilar to the powers enjoyed by the users accessing them. You might also say that this model was much more resilient as well, because, for instance, if an earthquake means that this server goes down, it doesn't touch or affect any of these other servers or any of these other users. So that was also another great property. And this was largely because there was no central point of failure. So there was not one single component in the system that you could take down, which would then subsequently take down everybody else. And for those interested in privacy, you might also argue that this had some really nice privacy properties as well, because rather than centralizing data in the hands of a small number of players. Instead, that data got separated across all these different servers operating by all these different people. So for those of you who are worried about privacy concerns, this is actually a much nicer model than what we have today. Because what we have today looks much more like this, where you have very large, very powerful players like Google and Facebook who are global in nature. And these global players, these hypergiants you might call them, accumulate users from around the world, such that rather than having lots of independent services with their independent communities, we have these global mega services which accumulate users globally. Now, it's really easy at this point to start to take pot shots at the likes of Google and Facebook and start to criticize this model. But we also have to recognize that there are some really nice properties of running a system like this as well. So for example, it's actually really nice to have a critical mass of users in this fashion. So for example, if I was to jump on a plane today and fly across to Mexico and I were to meet somebody, it's really nice that I could just add them on Facebook and know for sure that we'd be able to communicate wherever we are in the world. They also benefit from things like orchestrated deployments, because by having this one central organization that manages everything, they can try to build out their system in such a way that they really know for sure that it's going to give a great quality of experience to its users, and it's going to be super resilient. And this in part comes from huge economies of scale. Basically, as your system gets bigger, per unit, it becomes cheaper to run. So you can reinvest that money, get great engineering teams that build faster and better services that users like you or I enjoy. So with this in mind, I want to ask a simple question. Can we try to unify these models to get the best of both worlds? Now, I'm living in the UK, as you know, and you might note that we've actually been having some interesting political questions surrounding this ourselves. And what we found is that trying to get the best of both worlds is often not trivial, because as you try to push on one, almost inherently you push back on the other. So at this point, I want to get back to this concept of the decentralized web and what it means. So as I say, the decentralized web is essentially a bunch of open source platforms that try to give you decentralized versions and federated versions of popular services that we all know and use today, like Facebook, Twitter, and YouTube. So for example, this is PeerTube. So this is a decentralized version of YouTube. This over here, this is the logo of Mastodon, which is a decentralized microblogging service. So you can think of it very much like Twitter. And each of these platforms offer pretty much the same functionality as you get in the centralized versions, but they try to build it out in a decentralized fashion. So that probably sounds very abstract. So why don't we just quickly step through actually how these decentralized versions work. Now, for the rest of the presentation, I'm going to focus on Mastodon, which is a decentralized version of Twitter. But really, the concepts apply to any of the other federated platforms you may hear of, like Diaspora or PeerTube. Okay, so let's imagine we wanted to set up our own Mastodon platform. So the first thing we need to do is go and get ourselves a server. So that might be, a virtual machine running on the cloud, or maybe we purchase a bare metal server and install it in one of our university buildings. So once we've got our server, we then download the open source server software for Mastodon and we install it on there. Now, at this point in time, what we have is essentially like our own little mini version of Twitter. So this is just a simple microblogging platform. And this software that we've just installed is essentially a full stack web server, which gives you your own little mini Twitter. And of course, other people can be doing the same thing. So maybe this is my server in Queen Mary. Maybe Marco has set up another one in KTH, or maybe somebody down here has set one up in a company based in China. Now, once we've all set up our independent servers, what we can then start to do is accumulate users. So maybe we try to advertise that. Maybe I send a few emails on some mailing lists to tell people about this new server. And one by one, as people hear of it, they can come and join it. So they visit the server, they create an account. And once they have that account, they can then start posting messages and following people and the rest of it. And you can see here that all the other server operators are doing the same thing. So maybe Marco has sent some mailing lists, comments on the internal KTH mailing list, and accumulated these users. Okay. So the important thing to recognize here is that these servers are independent. They've been set up by different people, and they have different groups of users associated with them. So for an example, maybe this server down here is in Glasgow, and it's being used by Colin Perkins. So some of you might know Colin. He's the chair of the IRTF, and he's an academic up in Glasgow University. Maybe up here, John Crowcroft, he's joined my instance, and he's posting messages on there. So at this point in time, John and Colin are separate, they're independent, they're connected to other instances. Now, what you might want to then do is find a way that John and Colin can talk to each other. Now, the way Mastodon does that is through something called a remote follow operation. So what that does is on Colin's server, he can type John's username in. And what will then happen is a remote follow operation will take place here. And underneath the bonnet, what that means is the server will create what's called a federated link. So essentially, this is just a publish subscribe model where this server connects to that server. And essentially, whenever John posts a message, it will automatically be pulled across the network and presented onto Colin's timeline. So this is actually why we call this the Fediverse, or a federated network, because what's happening is these servers are now federating together. And as more and more users follow each other from across the different instances, more and more of these federated links will form to create a peer-to-peer model where these servers are all interconnected.
One question, Gareth. Are these servers more like, I mean, is one of these servers more like a Twitter or more like a thematic, I don't know, Facebook group page where there is like an administrator who set up the server, and then you have all users joining and they discuss within one single topic? I mean, are these many Twitters or are these like many pages, let's say?
So I suppose the best analogy is to say that there are many Twitters. If you have these instances, to you, it will look quite similar to how Twitter looks, where you can do a micro post and you can follow each people. That said, what tends to happen is many of the individual instances are set up on a given topic. So for instance, I might set up a server to do with academia or to do with communication networking research. And naturally, people interested in that topic are more likely to join it. There are generic ones as well, but often they're very topic focused. And to touch on the point of the administrator, yes, each instance is set up and operated by an administrator who is sort of responsible for moderating the content on there and ensuring everything is working smoothly. Yeah, from a cursory glance, it will appear to you much more like a Twitter platform.
Okay, and one more technical question: are these, each single server can be decentralized as deployment? Like it's not just on one virtual machine that you, as you said, you deploy it in just one geographical location. Can you have it in multiple locations as well, so that you get what the big ones are doing, right? Reducing latencies as well.
Yeah, so the simplest setup is just to be running everything on a single machine. But obviously, as it becomes more popular, you can actually decentralize it at the back end. So you basically a front-end load balancer with several instances behind. At the moment, there's not the type of sort of CDN model that I think you're thinking of. Rather, you'd have it located in a single data center with a bunch of servers sitting behind a load balancer. But you can, of course, use something like Cloudflare or another CDN to make sure that at least the heavy content, like the images and the videos, are served through that rather than through kind of a single data center location.
Okay.
But at least for the purposes of the rest of the presentation, it's probably easiest to think of one instance being just one virtual machine. Probably the easiest way to conceptualize.
Okay.
Cool. But yeah, I mean, one of the nice things about this model is that what you essentially get is a underlying decentralized platform with all these independent instances federated together. But logically, at least from the user's perspective, you have this sort of globally integrated platform where users on different instances from different parts of the world can still connect to each other and communicate. So this is a little bit speaking back to what I said before about trying to get the best from both the centralized and the decentralized worlds. So at this point, you might say, well, fantastic, looks good. We've now decentralized and everything working well. The only problem, though, is we have this Alexis de Tocqueville coming in from the side saying, actually, no, you've not. Because even though you've created this decentralized architecture and this decentralized design, it does not mean that it's naturally deployed and utilized in a decentralized fashion. Because, as I said earlier, there are often these pressures that push your model back towards a more centralized setup. So with that in mind, we thought, well, actually, why don't we try to measure Mastodon to try to get a handle on what type of challenges and what type of pressures exist when trying to decentralize. So what we did is we started connecting to these instances that are spread around the world. So we connected to about 4,000 of them. And as I say, a server is referred to as an instance. And for each of these instances, we connected and started downloading all of the content. So all of the tweet content. And in the world of Mastodon, tweets are referred to as toots. Okay. So for that, we got about 70 million different toots. And we use those to try and understand what pressures might be pushing back this decentralized web into a more centralized version. So the first thing to say is that we really found a growing system. So there's been a lot of buzz around the decentralized web. I'd be surprised if not at least a few of you have already heard of this. We saw increasing numbers of users. We also saw increasing numbers of toots and increasing numbers of federated links meshing all these servers together. So it seems really to us that this is a platform worthy of study. And what I want to do for the rest of this presentation is essentially go through a thought experiment with you. And the reason I say this is because a lot of the pressures in these social networks that push you back towards centralization are not created by the technology. Instead, they're created by the human behavior that uses that technology. So let's kick off with a simple one. So imagine you wanted to set up your own Mastodon instance. Where would you host your server? Where would you put it? Where would you run it? Well, of course, one option is for you to maybe buy a server and install it in your house, or maybe in your office space. But the problem is that's a very costly and complicated thing to do. So what happens instead? Well, we can measure this because we collected the data. This shows the top 5 hosting providers that we were seeing for the instances. Now, I just want to show you the color code because this is going to be consistent throughout all the graphs in the presentation. So the blue bar indicates the number of instances. The green bar indicates the number of toots. And the red bar indicates the numbers of users. And what you're seeing here is that about half of the users across the world's Mastodon instances are reliant on just 3 networks, primarily Amazon, AWS. And remarkably, 2/3 of all the toot content hosted in the world are based on those 3 networks. In other words, if just one of these networks decided, actually, it's against our terms and services to run a Mastodon instance on our platform anymore, a significant fraction of all the world's content and all the world's users would disappear overnight. So the extent to this is truly decentralized is actually a little questionable. So that's from an administrator perspective. Next question. Imagine you're a user coming in. Which instance are you going to join?
What do you mean exactly? Which instance would you join?
Well,
what are the options?
Good question. So in Twitter, if you wanted to join Twitter, you'd simply go to the Twitter front end, you'd create an account. But in Mastodon, because it's decentralized and you have these thousands of different instances, you have to pick one specific instance to connect to and then create an account.
How do you find out? How do you find out the instances that you said, like, if you were the administrator, you would advertise it?
Yeah, I mean, there's two broad routes. So the first one is through, say, word of mouth. So that might be via mailing lists or WhatsApp groups, or maybe just people telling you at seminars.
Mm-hmm.
And the second one is one of these indexing services. So for example, the indexing service we used was called NMM, social. And that essentially is like a little mini directory of all the instances. And if you create an instance and you want to publicize it, you can add it into this index alongside a few keywords, and people can come in and search for football or for technology, and they can find the links to your instance. They can then click on it, create an account, and then start using that instance. But naturally, this creates one extra level of complexity for users, because before they can create their account, they need to decide specifically which instance they're going to create the account on. So coming back to the question, which instance would you join? Well, what we find is that, unsurprisingly, the vast majority of users join those instances that already have other users on. So 90% of the users are joining just the top 5% of most popular instances. And this is what we call a network effect. The fact that there's users on there creates a gravity which attracts more users. Remarkably, the top 5% of instances host 95% of all the toot content. So this means that, again, if just one of these popular instances go down, you remove a significant fraction of the content. Now, there are many reasons for this, but I think one of the most interesting reasons is that different instances are themed around different topics. So here's a histogram showing, again, the number of instances, toots, and users using instances of a given topic. So you can see, for example, tech, games, art, activism, music, and so forth. And what we see is, perhaps unsurprisingly, over half of all the instances in the world are dedicated to technology matters. And that kind of makes sense, because still this is a relatively techie community. And it's not surprising that, of course, people setting up instances might also be interested in technology. But the elephant in the room here is that we actually see significantly different trends when we do not look at instances, but instead look at users. So for example, you might see this huge bar here. So whereas over half of all the instances in the world are about tech, they only accumulate about a fifth of the world's users. So they're disproportionately unpopular. In contrast, what we actually find is that about 60% of all the users are connecting to adult content instances. So these are instances associated with, adult material, which I won't go into the detail of. So in these cases, you have disproportionately popular instances. So even though only about 10, 15% of the world's instances are themed around adult content, they accumulate about 60% of all the users. So again, this raises big questions about actually how decentralized this setup is, because of course, if just a couple of those instances go down, they immediately take a large fraction of the user base with them. So at this point, you might say, well, all that makes sense. We understand that's just how humans behave. But because it's decentralized, at least it's reliable, right? Because we all know that decentralized systems are always reliable. Well, not quite, actually. So what we actually find is that 11% of the instances that we were looking at were inaccessible for half of the lifetime. And just to clarify, we were collecting this data for about 1.5 years. So it was not a short measurement period. So what we were doing is every 5 minutes, we tried to connect to all of the instances one by one. And then for each one, we recorded whether or not the instance was alive or dead. And what we found is that a significant fraction of them are going down regularly. Now, you might say, well, kind of that makes sense, because maybe some of the instances are very small or perhaps just run by volunteers. So what we then did was try to break down the instances into their popularity. So this is presented as a box plot of the downtime per instance, and we've separated the instances based on how many toots they have on them. So for example, this shows the downtime for instances that have 10,000 or less toots, whereas this one shows a downtime for instances that have over 1 million toots. And what we see is, fairly intuitive. So the small instances without much content tend to have more downtime. So they have a median downtime of about 12%, right? Over here, though, we see those instances that have over 1 million toots, the popular ones, have a much lower downtime, so they're more reliable. But actually, what's more interesting is to take a look at the outliers. And what we find is that across the popularity spectrum, we have instances that have got millions of toots on, but maybe in excess of 10 or 20% downtime. Now, imagine that from your perspective when accessing something like Twitter or YouTube. Imagine if a fifth of the time you tried to access Twitter, it was offline. You get frustrated pretty quickly. So we found that only 5% of the instances have an uptime that's similar to the things that you get with the hypergiants like Google and Facebook. Now, an obvious question is, why might this be happening? Now, there are a bunch of different explanations here, and there are thousands of different instances, and of course, there's a different explanation for each individual one. But what was kind of interesting to see is that in many cases, the infrastructures and the setups that they were using had inherent central dependencies that create resilience issues. So for example, I mentioned earlier that in many cases, instances are based on the same ASs, the same web hosting providers. What we found was a number of cases where entire ASs were going down, so they were going offline. Across our measurement period, we found 6 network outages, and those 6 network outages create hundreds of failures. And the way that manifests itself is a sudden drop in the number of instances offline. Because, for instance, if AWS has a network outage, literally about 30% of all the instances disappear instantly. So again, even though notionally the administrators running those instances think they're separate and independently run, because they've all put them on the same AS host, when that AS host has an outage, all of them go simultaneously. Another really interesting thing that we spotted as well is that many of the instances, a remarkable 85% of them, were sharing the same certificate authority. So they were using something called Let's Encrypt. And this is a really cool service that offers free certificates. Now, the problem, though, when using a certificate authority is that if the certificate authority has some problems, maybe it revokes your certificate, instantly you become inaccessible, because any mainstream web browser, when it checks that certificate, will say that you have a certificate error and it cannot be accessed. So what you can see here is a timeline across the measurement period showing the number of instances going down. And what you can see here around March is a massive spike. So about 100 instances went offline on the same day. Can anybody guess why that might be?
Revoked certificates or expired?
Yeah, exactly. So about 105 instances had their certificates expire.
Oh.
And what we then see is, of course, a little bit of time where people haven't really noticed, and then the number going down. And the reason this is going down is because obviously the administrators noticed and they're now fixing the problem. So they're renewing their certificates. Now with Let's Encrypt, they have a standard expiry date of 3 months. So you have to renew every 3 months. So what we can see is everything's looking fine and it's getting better. But then we get this massive spike again because the certificates again expire and you start getting TLS errors. So this is another interesting example of how the fact that everybody's using the same certificate authority with the same 3-month expiry date triggers these potential large-scale failures. So we've moaned quite a lot about the infrastructures and the dependencies that form. But the problem is it's not only issues there, because actually we're the problem as well, the users. We do not help with this question of decentralization, because in many ways, the way we interact as people is actually highly centralized in nature. So let me take you through what I mean by that. So imagine you've joined an instance and you now need to bootstrap your social network. You need to start following some people. You know, who are you going to follow? Well, we have this thing called network effect, where the rich get richer and the popular users get more popular. So what we find is that when a new user joins, they're disproportionately likely to start following another more popular user. And there's many studies that look at why this happens. But what we find is that the top 5% of users accumulate the vast majority of followers, such that you have, unpopular pigeons at the bottom with just one user following them, and then incredibly popular grumpy cats at the top with hundreds of thousands or even millions of followers. And this creates real issues because in Twitter, this is not too problematic. But in a decentralized system where all of these users are spread across different infrastructures, we have to ask, well, what would happen if Grumpy Cat's server goes offline? For sure, we know that it's going to have a bigger impact on the world than if Unpopular Pigeon's server goes offline. So this drives another form of re-centralization, simply because the users, through their follower graphs, are re-centralizing the social graph. And this is actually much more complicated than it looks at face value. So let me explain why that is. So imagine we've got 4 instances, and these are spread across 3 autonomous systems. So we've got OVH, which is a big French web hosting provider. We've got Amazon EC2, and perhaps at Queen Mary, I've got my instance running in one of the racks. And each of these have got their own body of users. And we can see they're all independent. And again, at face value, it looks like we're very decentralized. Now, what we might then have are these remote follow operations, which result in federated links. So for example, this user is following this one and this one and this one and so forth. So underneath the bonnet, what that means is that these servers are creating TCP connections between each other to pull the content across. Now, if this user wants to receive content from this user, obviously what needs to happen is this needs to be shared or retweeted across the social graph. And this obviously then results in these servers pulling it across one by one. So if this user follows this user and the content is shared across, in reality, what that actually means is a TCP connection is forming between these servers, and this one is pulling the toot across. Now, this is not a realistic social network. This is a realistic social network where you have a much more complex graph of connections. So for example, you have like really popular users over here. This is perhaps Marco, who's got lots and lots of people following him. We've got really unpopular users like this one. That's probably me with no followers whatsoever. And we have what we call bridge nodes. These are users who bridge between different communities. Now, these bridge nodes are really important for information dissemination because they're the people who can interconnect different communities. But what would happen if we had a network outage? So what would happen if somehow the network partitioned and this user got disconnected from that one? Well, all of a sudden, information can no longer flow. And this is why these users are so important. So essentially, the capacity to share information across the global network has been centralized on this one person here. And the failure of their instance or the failure of the network can massively disrupt this system. And this can be really damaging because what we find in Mastodon is actually most instances depend on foreign content. So that's content that's not generated locally, but which is pulled across the social graph by people like this. So you can see here that a small number, about 15%, get the majority of their content from their home instance, so they locally generate it. But the vast majority of them are actually getting the majority of their content from remote instances. So when you have those failures in the network, it really damages your ability to access information and share tools. So we thought, well, we can actually test this, right? So we have the social graph, we understand how Mastodon works. So we can run a number of simulations to see what would happen if certain instances failed. So what we did is we recreated the social graph and the underlying federation graph. And we simulated what would happen if one by one, we removed the top instances. And we then reconstructed that graph again and saw how well information can flow. Now, I'm not going to go too much into the metrics in case you've not come across these metrics before, but what we see here is essentially a slow, steady degradation in the capacity to share information. So as more instances are removed, the size of the largest connected component, so the ability to share all these items of content degrades dramatically. So removing the top 1% of accounts decreases this largest connected component, this largest part of the graph, down to about 25% of all the nodes. So that means 75% of the nodes, 75% cannot access each other. If we actually extend this and imagine we're having network outages, removing the top 5 networks actually shatters the social graph into hundreds of different components. So each of these different instances become disconnected and can no longer communicate whatsoever. So this is really problematic for the idea of having a globally connected system, because these small issues, these small network failures can have massive impacts because of the way that our social networks are wired and the fact that we have a small number of users who interconnect everybody else. So we can also check here at what happens to the content, because that was just the social graph. So again, what we show here is what happens to the amount of toots being available if we start killing instances and networks. And what you can see here is as we remove networks or as we remove instances, the availability of the content just plummets, such that if we were to remove the top 10 networks in the world, we'd only have about 15% of the content left. There'd be a total and utter collapse. Equally, if we remove the top 50 instances, you'd have similar levels of unavailability. And remember, we're talking about 4,000 instances here. So by just removing the top 50, we kill about 80 to 85% of all the content there. So what we thought is actually, how can we go about trying to improve this design such that when failures happen, the system remains resilient? So what we did is we turned back to the ancient and very tried and tested technique of caching and replication. So what we tried to do is have a subscription-based replication service where whenever you follow a user on another instance and they post something, you make a local copy on your instance. And you index that such that if the original instance goes down, everybody can get the replica from you. So it's very much like the old-fashioned peer-to-peer systems where everybody shares content and anybody who's got a replica can be accessed. What we found was that with just a relatively small number of replicas, we can dramatically improve availability. So you can see that here with the subscription-based approaches, the lines are significantly higher than without any replication. So in other words, there's far less toot unavailability if we do the replication. All that said, you'll notice that we still have a significant fraction of unavailability. So even when doing this subscription-based replication, if we remove 10 of the top instances, availability drops to around 70%.
One question, Gareth.
Please, Michael, yeah.
For replication, I mean, would this mean overhead, storage overhead for all the other instances? Since you need to replicate the entire content, and those instances, you said some of them are very small, voluntary run. Is this creating a scalability problem to solve?
Yeah, I mean, it raises a bunch of questions, particularly for storage, but also for compute power as well, because obviously if you're serving as a replica, there's a chance that somebody else might connect to you to access that item of content. So it does create some resource questions, and those resource questions are exacerbated by the fact that we have the power law distribution of the social graph again. So what that means is that if I'm a popular instance, I'm probably federated with other popular instances. And that means the burden of replication is going to disproportionately fall on us. Because if I've got 1 million users and you've got 1 million users who all follow each other, essentially all of your content is going to be replicated on me and all of my content is going to be replicated on you. So it basically exacerbates the problem further. The other issue is that, well, actually, if you think about how these instances might run, we might have other reasons why burden is disproportionately shared. So let me just remind you, this subscription-based replication does improve availability. So pairing it to this graph with replication, we can see that unavailability is much better when we do replication, but it's not perfect. It's still losing tens of % of content. And imagine you're accessing Twitter, and each time you visited Twitter, 10 or 20% of the things that you wanted to see were not there. You would not be happy about this. And the reason for why this occurs is actually precisely what I was mentioning a moment ago in response to your question. There are reasons why instances that subscribe to each other might go down at the same time. So imagine you're a Japanese speaking instance. The chances are all the users on your instance speak Japanese. And there's a good chance that all the other instances with users that they follow will also be those that speak Japanese. So if I'm in Japan setting up one of these instances, there's a good chance I'm going to go to a web hosting provider, which is based in Japan, in which the language of the platform and so forth is in Japanese. So disproportionately, it's very likely that those two instances are going to be hosted on the same network provider, like Sakura, which is a big Japanese hosting provider. So if one instance goes down because the network has an outage, invariably the other one that's replicating your content will go down at the same time because they're hosted in the same place, which is why when we remove lots of ASs, availability is badly affected because the replicas that we've chosen to have are often hosted in the same network as you.
Mm-hmm. And here, when you remove Amazon, you remove the entire Amazon, right? Or it's not like just, okay.
Yeah. So essentially, when we say AS, we're referring to literally the AS. So it's not like
Mm-hmm.
in the network in any way.
Yeah, okay.
So this is an inherent issue with the social network, right? Because we know the social network has these type of weird social biases. So what we decided to do is try to find a way to disambiguate the replication from the social graph. So we proposed a very simple thing. So how do we improve this? Well, let's try something with random replication. So rather than tying the replication into the social graph and pushing it to your followers instance, why not just randomly pick an instance in the world and put it on there? So you can see here that this is without replication. So as instances get removed, availability drops dramatically. This is subscription-based replication, where we're putting it onto the instances that follow us. And this is random replication. So what you can see is that the unavailability is pretty much zero. So we get about 99% availability with random replication. And the reason is we disconnect the choice of where we replicate from issues such as placement of the servers or the social network. And actually what we find is really good performance benefits here. So I want to conclude there. We did a bunch of another analyses and they're all in the paper. I strongly encourage you to take a look if you're interested. But I want to conclude by making a couple of points. So the first one is that decentralized designs and decentralized architectures do not necessarily mean decentralized deployments. And what will often happen is the pressures of social behaviors and human behaviors will push these decentralized models back to a centralized version. And that's what we started to see in some of these D-Web platforms. And because of this, at least from my standpoint, I think we need much more of this measurement-informed development, where when we build these systems, we actually continue to measure them in the wild to understand how users are using them and how that's undermining our initial assumptions in the system. And to conclude, it's basically damn hard to decentralize the web. Thanks for listening. And if you have any questions, I'd be very happy to take them.